This morning we're looking at Chapter 31, which is based around networking. Now, I know that all of you have had your intro net web class at the beginning of your program, and I've heard you guys talk about how you have to rotate your laptop to get a signal, right? That's your big takeaway from that course. Part of this chapter, just like the one on databases, goes through some of the rudiments of how networking works, and it's a very brief fashion. You guys should understand, I'm hoping, what TCP/IP is, right? And do you know the difference between what TCP is versus IP? What's an IP?
Internet.
Right. And when you say you got an IP address, what does that mean?
It's a hardware address. It's a unique address.
It's not a hardware address. Nope. A MAC address is a hardware address. Every network device hypothetically has its own unique MAC address. The one thing I always tell people, though, is they can be spoofed. In fact, some better devices will have that as an option by default, so that, you know, if you spoof your address, then people can't hack you as easily. But an IP address is an address that's issued either by a server or hard-coded for your device on a network so that your device is addressable and traffic can move back and forth to that device. So what's TCP then? And what's that responsible for? Yeah, so IP address deals with what technically? Remember your OSI layers? Did you guys learn that stuff? What works at the bottom and what works at the top?
I think the IP address is close to the top. Yeah, the IP address should be close to the top because you're getting it, it's being generated dynamically, isn't it?
Well, depending on how you're looking at the levels, if the first level of the OSI is at the bottom, what's at the bottom?
It's going to be the computer, or should I say the MAC part.
Physical layer.
Yeah, it's the physical layer. An IP address operates just above the physical layer, so it's at the bottom. So the device has to have a network interface. It gets issued an IP address, either hard-coded or dynamically, and then the transmission control protocol operates over the top to actually move the data. And the reason we talk about these things is you do need to know how to connect to a device over a network in order to be able to have it communicate, or at least have a rudimentary understanding of what an IP address is and you know, what some of the protocols are. Is TCP the only protocol that operates over IP? Absolutely not. HTTP is a protocol, FTP is a protocol, UDP is a protocol, yada yada yada. There's many of them. Okay, so the IP is responsible for the physical layer. Now, most of what we're going to do here in this chapter really stems around the concepts you see on this slide. What we're going to do is actually fairly simplistic in terms of the difficulty, I think. The exercises that we're going to perform in this chapter, one is going to mimic what you'll see in the slideshow and then in chapter. In fact, it's very, very similar. So it shouldn't be that difficult if you follow the examples. The point is that we're going to write two programs that will run together. We don't have a Java server running out on our network that we can connect to, so what we'll do here is we write two programs that will talk to each other. But in essence, it really is simulating the same thing. It's just happening on the same computer instead of over a network, but the concept is in essence the same. Now, that seems kind of like a trivial thing, but it's actually pretty important, because this is really what happens when we use the internet. We are interfacing with a server. We send requests to the server, we send information to the server receives it, it does something with it, and it sends it a response, hopefully. Right? And if you think about that, so we have something happening on our client, we have something happening on our server. Hypothetically, they're separate machines. It could be the same machine, right? Think of like when you run XAMPP as a web server. It's on your machine. But really, it's two separate programs running and interacting. So that's really what we're focusing on. The thing that you're going to notice is as you're writing these programs, you'll write a server component and a client component. Is you'll always have to start the server first before the client can connect. So one of the problems you might run into is you started the client first and not the server. And if you think about how servers operate, we just expect servers to be up and running all the time. It's kind of a given. You know, are servers in reality running all the time?
No.
No, they have down periods. One of the reasons so many of the web servers out there run on a Linux platform is because Linux is a whole lot more stable than Windows, or at least it used to be. 10, 20 years ago, they were significantly more stable. You know, and then, excuse me, that's pretty significant because if you can keep an operating system up and running, users have a higher satisfaction level. One of the reasons why Linux is more stable is because of the capability of actually patching the operating system and the software without necessarily needing to restart the server, meaning the whole operating system in the machine. The only time you really need to reboot a Linux machine is when you're reworking the kernel being the core of the operating system. If you remember from that little movie tidbit I shared, and it did kind of lose my train of thought there a little bit. All right, well, anyhow, kind of stemming a little bit beyond this whole like Linux discussion, let's move on to some of the other things that we're going to look at. So here's actually a little snippet of code, and in terms of like the general operation of how we do client-server communications, this is a small microcosm of a working application. Obviously, if you're doing something more programmatically advanced, you'll need a lot more code. But the code that is bolded is, you know, the key part of it. That's where we set up the connections. So you can see that there's actually what we call server sockets and sockets. If you're familiar with port addresses with the IP address range, so anytime you have an IP address, you also have, what is it, 65,537 ports also available to each IP address. So that's equivalent, you know, to, you know, think about it in terms of like little storage spots, right? So those are all these different ways that you can connect to the same device through different channels, basically. So when we are surfing the web, we typically use port 80. That's the most common port. When you guys do your SSH, it's on port 22. When you do your FTP, it's on port 21. When you do your email, it's on port 25 or 487 or yada, yada, yada. And there's all these programs that use different ports by default. MySQL, for example, uses 3306 as its default. You can tweak any protocol to run over any port, but we have certain ones that we use in commonality. So that is important. So one of the things that happens is we establish sockets so that we can attach to particular ports, so that we can move the communications. On the server side, we set up server sockets. We indicate ports. On the client side, we set up a socket. All right. So for outbound and inbound communications, we indicate what host we're connecting to and which port address. All right. So you'll see how that works. The other thing that they have here are these data input streams and output streams. And if you learned a little bit of file I/O when you did your Java 1, which I'm hoping you did, and it might not have been very deep level of it, the data stream, in terms of how a computer looks at it in a running application, it doesn't really see much of a difference between information traveling in and out from a network or from a file, because once it's reading the information, it's being streamed in one way or the other. You know, the data is being read typically in a sequential fashion. Right? And that's why we call it a stream. Right? It's one bit after another in order. Now, if you think about how a network works, and I'm hoping you were taught this, Like if I take an email message and I send it, I have a piece of information that's so many bits or bytes or megabytes in size. When I hit send, it's not necessarily sending it bit by bit in that order. It breaks it apart into packets, right? And then it goes to the destination, and the destination reassembles it. So it's not arriving all at the same time in the same order. It's pieced back together. A stream, however, does go bit by bit, and that's how the information comes in. All right. So the other part of it here is you will do this little command here to be able to send information, depending on its data format, to the server. The server will then read it in the appropriate data format, do whatever it does to it. I mean, they just show it as like going out and coming back. But you can imagine that if you're sending something to a server, you're doing it because you want something to happen. So on the server side, you'll have a program that will handle whatever's coming in, does whatever it does, generates some sort of output or response or whatever, and then it will come back using this approach. So you see how there's a commonality between the output statements, right? And this is a primitive example, but it gets the point across. And then when it comes back over to the client, then the client can grab that and then do whatever it does with it. And, you know, putting it up on the screen is, you know, one of the more rudimentary tasks that you do, but it's enough to show that it's working. So our in-chapter example will basically show you something that simple. The exercise, plural exercises, one will do a very similar, simple type of connection with a little bit of programmatic logic on each side. And then the second exercise, we'll step it up a little bit, and you'll see a slide in a few moments, where instead of just passing little bits of information, we're passing objects. And both of those concepts are important. All right. We have a little thing here. It says, problem, write a client to send data to a server. Server receives the data, uses it to produce a result, and then sends the result back to the client. What I just said, right? Very, very simple approach. In this case, you can do it on the console level, but you can also do it on a graphical level, which is really more the focus of the chapter. If you kind of break it down into the flow of it, you know, using more of like a UML type of approach, this is kind of what it looks like. So one is the transmission out, one is the transmission back. Notice the placement of the various components and how they're similar on both ends. It's just the perspective from which you're operating. All right. One of the chapter examples is this right here, and I think that what would be good is as soon as we finish the slideshow, we'll come back and try this and get it to work. I'm going to opt to work inside of Eclipse for this one, and that's just a personal preference. But you'll get something that looks very much like this as a result. You can look at the code that goes with if you want. I'm not really concerned about doing that at this point because we can just pull it up from the chapter. One thing that is also available to you when you're doing this type of work is there's classes that are built in to do all sorts of things. And you should realize that whenever you connect to a web server, logs are kept. Most, you know, default hosting environments, and Kronos is even one of them, where we run logs that just continuously keep track of what you're doing. You know, what IP address came and accessed what resource? What time did it happen? Yeah, and yeah, well, we don't keep them forever, obviously, right? They run for a while. Kronos is not that busy of a server. But it's one way to keep track of who's visiting your system, where the traffic is coming from, and actually a really useful tool for troubleshooting, because if you have a problem, you can see that a page request is going in and the server's not responding. Or you can see what person went to the website or your server and tried repeatedly to crack a password, for example. So they have this class that's built in that will actually grab the IP address of whatever user or system is coming in. So that can be used in a lot of different capacities. Another thing that you can do is, the more simplistic example that we have here is one client and one server, but the reality is that servers often are working with multiple clients simultaneously. We kind of take that for granted. So the server's got to be able to handle that. It's also got to be written so that it can handle those things. And the way that we do that, and we haven't talked about this yet, is we set up sockets, but we also set up threads so that each interaction with a separate client happens on a different thread. A thread, if you're not familiar, is basically a stream of a program running. So it's like one instance of it, and we can have multiple threads working at the same time. Okay, so we will get to that chapter that talks about those things. At this point, this isn't going to be relevant to you unless you do the extra credit, which I encourage you to do. It's an easy way to get a point if you have the time. That's kind of a caveat there. But it's a fun one if you can do it. All right, just a little graphic of multiple clients. Of course, the server has to set up multiple sockets for each client, and then also has to let go of those sockets when the communications are done. Well, there's better ways than others. Think of like MySQL, it's really polite to close a connection, but some people don't do it. So the server has built-in timeouts. So let's say if there's no response for 30 seconds, it'll just say, okay, whatever, bye. And that can be controlled as well. So, the answer to that is kind of multifold. There is some automatic control of that, but it's usually better. It's considered elegant and polite to close your session. Same is true like when you do PuTTY, right? A lot of people just hit the X. Linux servers don't really like that. They've been modified over the years to allow for it to happen a little more intelligently. But in the past, it was considered very poor etiquette to just, close the window or walk away. So, all right, so let's move on. Actually, we'll look at this one. All right, so one of your other assignments is going to be based upon actually passing objects to a server and back. So instead of just passing a little piece of information, we are passing an entire object with its methods, with its attributes, all intact. Now that can be powerful because really it allows you to send a whole bunch of stuff at once, or the uniqueness of whatever that object is. So if you make an instance of something and it's got its own unique properties, to be able to just take that whole thing and move it somewhere, do something with it, and bring it back. That's pretty powerful. Once again, I'm not going to do the example here. Our extra credit assignment is to do this. And all the code's provided. It's a lot of code. When there's a lot of code, there's potential for a lot of problems. So one of the challenges there, if you want to undertake it and you have the time to do it, would be to get this program running. And you see that it's a distributed game, right? So it's going to require multiple connections to make, to be distributed, basically. So that one I'm allowing you to work as a team if you wish to make it work, and then everybody in the team can submit it separately and earn the points. The way that I would grade this one is that you get it working, you show me that it's working, and then you do a little submit saying I showed it to you, it was working. Okay, give me my points, please. So that's the way that one will be graded. So it'll be kind of treated like a lab assignment. It's not required, but if you have the time to do it, get the point, go for it. They do walk through how it works here. You want to just take a look at that. Remember, they're doing UML stuff for your Java competition, right, at the AITP. These are UML diagrams. So what they might have you do is just have you logic through how things actually work. I'm not going to spend any time talking about that. Just very quickly on this next topic area, because none of your work really focuses on it, but it's not bad to be exposed to at least the concepts. So we have these two different type of sockets. There's the stream socket and the Datagram socket, and that's kind of a difference between like what I was trying to point out before, where you get some information and it streams, so it comes in serially, one bit at a time, in the order in which it's in the file, right? And then we get the Datagram approach, which it chops it up into pieces, it gives it an address, origination, destination, goes there, and then it gets reassembled. And both can work just fine. And there's a little bit of issues with it, and you see what they're suggesting is that you use TCP, because TCP has built into it error checking. It has a little bit more file packet overhead. So in other words, every little bit, even if it's streaming in, has a to and a from address and a time to live and all these different components, and then the content itself, where UDP is actually a little bit more efficient in its addressing structure. So if you're moving a really large amount of data, every time you remove some of the extraneous header information for each little chunk of data, it actually is more efficient, provided your connection is good and you don't have problems with it, because it does not have the error checking built in that TCP does. So just to know the difference between the two. There's, this slide makes it seem like UDP is a bad thing. It's not a bad thing. It's just different. It's a different approach. Generally speaking, if you have a good connection, UDP is actually a lot more efficient. Just like FTP is a lot more efficient at moving files than HTTP, because once again, it has a smaller overhead. All right, they go into what's in a Datagram packet. That's fine if you want to study it, and they go into a little bit more depth, and that's basically all I'm going to talk about in the chapter. So if you want to play with the Datagram stuff, go for it. That's not my focus here. My focus is client server, moving objects, moving data, and getting things to communicate. It really is not that difficult of a chapter. So I'm hoping this one you guys will be able to knock it out pretty quickly. So now that I'm going to be completing this PowerPoint here, what I want to do is go into the examples of the client server thing, and then I'm going to let you guys carry on with your own work. So you can get the first homework assignment is not dissimilar from the sample in the chapter. The second one, you'll have to go back to the chapter, look at the example, and then build that capability to pass objects. Once again, I don't think it's that difficult. You may differ on that. I think actually the hardest one is getting that tic-tac-toe thing to work, because there's so much code to paste in, and being able to test it. That's why it's extra credit. All right, folks, that's going to end the brief lecture here, so we can get working on doing this stuff for real.